Good afternoon to one and all. We will begin with the session, and I would warmly welcome our participant and our today's expert, Engineer A. Purohit sir. I would like to introduce sir as Engineer A. Purohit is currently working as scientist E at CWPRS Pune. He has been working in the field of coastal engineering at CWPRS for more than 28 years. He has completed his bachelor's degree in civil engineering and master's degree in structural engineering from College of Engineering Pune and stood in the rank of merit. Sir has worked in private firm as structural designer and designed structure for prestigious projects like GMRT, design of 158 buildings using prefab technology for Sidco Mumbai. He has published over 52 papers in national and international conferences, journals in the field of coastal engineering, and also has been a peer reviewer for publication of papers in national and international conferences journals. Sir has been a member of committee constituted for public interest litigation PIL in the year 2013 for dredging related case in Mumbai High Court. He has attended about 20 conferences, workshops at national and international level and delivered more than 45 lectures in coastal engineering to the practicing engineers at National Level Institution of Engineers, IIT Bombay. Sir has been nominated as an expert for high-level committee meeting at national level and technical advisory committee meeting of state government for representing CWPRS. He has provided design for many prestigious projects. Few of them include Navi Mumbai International Airport, 26-kilometer long Mumbai Trans Harbour Link Bridge, Mega Port, and many others. He is a member of various technical bodies which include Institution of Engineers India, life member of Indian Society of Hydraulics, etc. We are glad to have such an eminent personality with us today. I request Sir to begin with the session. I am certain that this session will be beneficial to all our participants. Over to you, sir.
Thank you, Aboli madam. Are you able to hear me?
Yes, sir.
Thank you. At the outset, I would like to thank the management of Dr. D.Y. Patil Institute of Technology, Pimpri, and Dr. Deepa Joshi Madam, HOD Civil, Professor J.D. Agrawal, for inviting me to deliver this lecture in 2 days seminar in coastal and overview. I also would like to thank Director CWPRS Dr. R.S. Kankara for granting me the permission to deliver the lecture on the topic Physical Hydraulic Modeling Techniques in Coastal Engineering. Now I will share my presentation. Good afternoon. The topic on which I will be delivering the lecture is Physical Hydraulic Modeling Techniques in Coastal Engineering. Well, we know that in our solar system, there are a number of celestial bodies as well as the planets. Among these planets, Earth is a planet on which we are living. And this Earth surface includes 70% of the water, and the life exists on the surface of the Earth because of the presence of this water. Well, we know that ocean, as I told you, that about 70% of the Earth's surface is covered by the water. The water which is there in the oceans as well as in the rivers and lakes, they will get evaporated. And after getting evaporated, it goes up into the sky and gets condensed, and then it gets converted into the clouds. And after it gets the appropriate conditions, then it will start precipitating. And then that water, once it will start precipitating on the hills as well as in the jungles, and then some of the water will get absorbed in the ground, some of the water will fall, start passing through the rivers, and then these rivers then meet the ocean. And during in the upper reaches of the river, the flow is quite turbulent in nature, and even you can see the big boulders, they can also be transported. And once these rivers travels hundreds of kilometers of distance, then it brings a lot of sediments, and then that sediment is carried. And when that sediment is carried and when the river meets the ocean, that sediments gets deposited in the ocean. So when the rivers, they are meeting the ocean, the type of sediment which comes into the ocean is a fine material, maybe say clay, silt, or even the sandy material will be also there. Then this metal which gets deposited into the ocean, say consider for example of the case of a Mumbai, where the Mumbai port is situated on the leeward side of this artificially developed island, while there is another port, what is called the Jawaharlal Nehru port, which is established on the opposite side of the Mumbai, and this entire region is called as a Thane Creek. So when the water level in the ocean rises, naturally the water will start coming from the ocean into the Thana Creek area. So such type of flow is called as a flood flow. And afterwards, when the water level in the ocean starts falling down, the water from the upper reaches of the Thane Creek, it starts coming down. So there is a continuous process of flooding of the water into the creek. After about 6.5 hours, again the water will start coming out of it. So the sediment which gets deposited into the ocean, you can see here the material during the flood tide, it comes into the Thane Creek. During ebb tide, it comes out of the creek. So whatever the development you are proposing in these areas, as the sediment moves to and fro into the creek area, whenever there is a deepening of the channel has been carried out for the movement of the ships, or some berths are constructed where the sufficient depths are maintained, called as the berth pockets, and in the dredged area that sediment gets deposited. No, so this is the one part, that the river brings a lot of sediments, that sediment gets deposited into the ocean, and then that material moves in and out of the creek or in and out of the estuarine region. And then whenever there is a increase in the depth, which has been artificially maintained by the port authorities, that sediment gets deposited into it. So we have seen that there is a rise in water level, fall in water level, what is called as a flooding and the ebbing. Similar to that, the waves are also formed in the ocean. Now we know that this is the Earth's surface, and at the equator we know that the temperature is maximum. So you can see here at the equator the temperature is maximum, that about 25 to 30 or even more than that. And at the North Pole and the South Pole, the temperature is minimal. Even it goes below zero, maybe say 40 degrees, 50 degrees or so. So because of this, there is an unequal heating of the Earth's surface. And because of this unequal heating of the Earth's surface, what happens that the temperature gradients will get formed, and the colder air being a denser, and the air which is at the equator being warmer, it goes up into the sky because it is a lighter one. So naturally, to have a balance, the colder air from the North Pole as well as from the South Pole will start moving towards the equator. In addition to this, the Earth is rotating about its own axis, what is called as a Coriolis effect. So because of that, what happens that the temperature gradients get converted into a pressure gradient, and from that, because of the pressure gradient which gets developed, the cyclones will get formed. So we know that the Earth is rotating in an anti-clockwise direction. That means from the west to east. So from the North Pole, wind will start blowing towards the equator. It will get deflected because of the Coriolis effect. So the cyclones will get formed. So when you consider the cyclone, this is called as the eye of the cyclone, maybe having a radius of about varying between say 10 kilometers to 40 kilometers or so. And at the outer periphery, the distance may be say 1000 kilometers, 1200 kilometers or so. So it's a very huge energy which is there in the cyclone. And then these cyclones which are there are getting formed because of the pressure gradient which gets developed. So you can see at the center, the pressure gradient may be of the order of about 900 hectopascals or so. And as you start moving out of it from the center towards the periphery, the atmospheric, it starts going or it starts increasing towards the standard atmospheric pressure, maybe say 1006 hectopascals, or we can call it as a millibar. So some sort of a pressure gradient gets developed. If this pressure gradient is very steep, naturally the wind which will be generated because of this pressure gradient will be too strong. So you will see that here, when the cyclones are getting generated, you can see this is the eye of the cyclone. No doubt it is rotating about its own axis, but it also has a forward movement also. So this energy which is there in the wind cyclone is getting balanced in the form of the wind velocity plus the forward movement on the right side, while on the leftward side it will be the wind velocity minus the forward wind speed. So such cyclones which are getting generated in the ocean, they are classified as depression, storms, severe storms, cyclones, super cyclones, and so. So this India Meteorological Department, they have classified that when the wind speed in the cyclone is less than 62 kilometers per hour, it is called as a depression. But when it is between 62 and 87, it is called as a storm. So normally when the wind speed between 62 to 87, normally the storms, they are called as a storm. When it goes between 87 to 117, it is called as a severe storm. If it is between 117 to 200, it is called as a cyclone. So cyclone is a local synonym to the severe most storms which are getting generated in this area. So as far as United States is concerned, these cyclones, they are called as hurricanes. In India, it is called as a cyclone. So what is a cyclone? Cyclone is nothing but sort of a coil of a snake. So it is rotating in a particular direction in the form of a snake type of thing. In Australia, you will see that in Australia, it is called as a Willy Willy, while in Japan, that is nothing but in the Pacific Ocean, it is called as a typhoon. And when this wind speed increases about 200 kilometers per hour, it is called as a super cyclone. So such a type of super cyclone has occurred in the Indian Ocean in 1999, which has started from, I think, maybe say from 24th of October. So at that time, it was a depression, and then slowly it starts building up. And then when it starts building up, it gets converted into storm, then a severe storm, then a cyclonic conditions. And when it reaches to the Paradip port, which is there in the state of Orissa on the east coast, it got converted into what we call it as a super cyclone. So you can see that what are the factors which are affecting these factors which affects the wind which is getting generated because of these cyclones. So it depends upon type of cyclone, whether it is a depression, whether it is a storm, whether it is a cyclone, or whether it is a severe storm, or it is a super cyclone and dust. It also depends upon what is the wind speed. It also depends on the duration for which the wind is blowing on the surface of the sea. And it is also it also depends on the distance over which that wind is blowing. Suppose if the wind is getting generated and if it is blowing over an area of about 1000 kilometer radius, then that distance is called as a fetch. And the point from which it is under not the influence of the wind because of the cyclone, that distance is called as a decay distance. That means the point from which the waves which are generated, they starts propagating on their own because of the momentum it had gained, is called as a decay distance. So we can see here that how the waves are getting generated. As I told you here, then the wind is applied when the wind imparts its energy to the water surface. And so during cyclonic conditions, the wind is blowing from all direction because it is in the form of a circular motion, and so the wind is acting from all 360 degrees direction. So naturally the waves which are generated, they are confused. So that means the continuously wind is acting and a wave is generated. So it is a confused sea state is there. So that confused sea state, I can show you that over which the wind is blowing. So the waves which are generated are called as a gravity wave, because the source for this wind, the source for this wave is nothing but the wind, because the wind imparts its energy. So there has to be some action, and to that action there is some equal and opposite reaction also. So the wave which is generated, how that when that wave will start moving, it will come to an end after traveling some distance. What is what is an opposite force which is acting to the direction of the wave is nothing but the gravity. And the waves which you can see with your eyes in the ocean, it will, you can see that these waves, they do have a wave period varying between 6 seconds and 20 seconds. So the waves which are under the influence of wind which is there are called as the seas, called as the seas waves. Waves in the generating area are under the influence of wind. So steeper, so these are the waves which are very steep. That means its slope is very steep and it will have a shorter period. So I can say that the wave period may varies from say 4 seconds to 8 seconds or so. So the type of waves which are generated, or what we call it as a wave climate. So the sea is quite in confused states because the waves are coming from different directions. It will have different wave heights. It will have different wave periods. And these waves are generated from all directions. So if you try to plot a graph of wave energy versus frequency, so naturally the waves in the ocean, they are not monochromatic waves, but they are the random waves. That means each and every wave will have a different wave height and different period also. So if you try to plot a graph of wave energy versus frequency, as the waves are coming from different directions, it will have the number of peaks. So it's a multi-peak spectrum, or what we call energy is distributed over a range of frequencies, and it will have multiple peaks. Now, once these waves they start leaving the generated area, and they are no more under the influence of cyclonic conditions, then you can see that when the waves propagate towards the coastline, these waves will like as a uniform type of waves, they are propagating towards the coastline. So the wave climate is uniform. That means the waves are coming only from particular direction in a particular time. So the wave energy spectrum, you will have a single peak. So the wave propagation towards the shore is a unidirection, and the spectrum is with single peak. So such type of waves they are generated. Now, once these waves, they will start coming to the coastline, naturally they will be under the influence of the depth of water through which these waves they are passing, and they are coming to the coastline. So when the waves are coming towards the coastline, a depth will occur at which the wave will not propagate, but it will break. What is called as a breaker zone, or what is called as a surf zone. So these waves, when they travel from deep water or maybe say intermediate water depth, and when they start coming towards the coastline, the waves will get refracted. I think in school days, we have learned what is refraction. So refraction is nothing but when a ray of light passes from one media into another media, it changes its direction because of the difference in the densities. The similar is the case here. Here, instead of ray of light, it will be a ray of a wave, and the depth is nothing but the different densities. Or so based on that, you can see that the waves will get refracted, and these wave ray will try to align themselves perpendicular to the bottom contours. So you will find that these waves, when they comes to the coastline, they will align themselves perpendicular to the bottom contours. So what is called as refraction. So when these waves they are coming towards the coastline, there may be say headlands, there may be say some bays and all these things. So at the headlands, the bottom contours are something convex type of things. So naturally the wave energy will get concentrated. So there will be increase in the wave height. While in case of waves, the wave rays will go away from each other. So there will be reduction in the wave energy. So naturally, whenever there will be reduction in the wave energy, the wave height will be less. But at the headlands, there will be increase in the wave energy. That means increase in the wave height. Now, once these waves are coming in contact with some structures which are constructed in the coastal areas, maybe say breakwater structures, maybe say wharfs, then the wave energy gets laterally spread along its direction of propagation. That means the wave energy will get diffracted. So that is what is called the diffraction of a waves. So if on the leeward side of such structure, the wave energy is less. So there is a calm energy, and you can plan your berthing structures in this area rather than planning it in this area. Now, similar to that, when the waves they come in contact with the structures like rubble mount structures, so this is an incident wave height and this is a transmitted wave height. So naturally, some sort of energy will get transmitted through the body of the structure because these structures are porous structures. So that is what is called as a wave transmission. Similar to that, there will be wave breaking also. So when the bed slope is flat, maybe say flatter than 1 in 100 or so, the type of waves which they break are called as a spilling breaker. When it is relatively steeper bottom, maybe say between 1:30 to maybe say 1:50 or so, the waves which are there, you can see they are called as a plunging waves. And when the beach slope is far steep or very steep, naturally the waves will break as in the form of a surging. Then the another important, so we have talked about sediment transport, we have talked about waves. Now we are coming to the thing what is called as tides. Well, in the school days, we have learned what are the tides. Tides are nothing but the rise and fall of the water level in the ocean surface. These tides, they are generated because of the gravitational pull exerted by the sun and the moon on the surface of earth. That means on the rotating surface of the earth. So when the sun and the moon, they are in one line, the force of attraction is more. Similar to that, when the moon goes at quadrature, that means at 90 degree with respect to that of the sun, then the waves which are, the tides which are generated are called as the neap tides. So when both sun, moon and earth, they are in one line, the force of attraction is more, called as a spring tide. But when the moon is at quadrature, that means at 90 degree, the force of attraction gets divided into two different things. So it is called as a neap tide. So one tidal cycle, you can see that as far as various oceans which are there on the earth is concerned, there are some areas where the tidal duration is of the order of 24 hours and 50 minutes. That we know that our day cycle is 24 hours. But the tidal cycle, you can see here, is not 24 hours. It is 24 hours and in 50 minutes, because by that time it comes to its original position, the location on the map of the earth has been shifted by about 50 minutes because the moon is rotating about the earth. So the tidal cycle is 24 hours and 50 minutes. So in some areas on the map of the world, such type of tides are generated. Say, for example, in case of Bay of Fundy in Canada, the type of tide is a diurnal in nature. That means there is only one high tide and only one low tide. So in 24 hours, 50 minutes, there is a high tide and low tide. But as far as the Indian Ocean is concerned, the type of tides which do prevail, they are semi-diurnal in nature. That means in a tidal day of 24 hours and 50 minutes, there are two high tides and two low tides. That means if you consider one cycle or half a cycle of it, it consists of 12 hours, 25 minutes. So in 12 hours, 25 minutes, there is a one high tide and one low tide. That means the flooding takes place half of 12 hours, 25 minutes. It means it is for 6 hours, 12 and a half minutes. So for 6 hours, 12 and a half minutes, the water goes into the estuary. After 6 hours, 12 and a half minutes, again the water comes out of the estuary and it goes into the ocean. So these are what is called as a tide. So that's what I've seen when they are in line. That means moon, new moon and full moon, they are in line. It's called as a spring tide. That means the variation in the low water and the high water is maximum. While when the moon is at quadrature with respect to that of the sun, the force is getting divided into two opposite directions. That means at quadrature direction. So the tidal ranges are less. So this is a continuous process which is going on. The moon is rotating around the earth, and this earth moon system is rotating around the sun. So there is a continuous change in the water level in the ocean surface. So this is what is called as a tide. So why we have to study this? Because the thing is that we have to deal with the development of the facilities to be created, or the facilities which are to be created in the coastal areas. So it is very essential that we should know these different phenomena. So you can see there are lowest astronomical tide, highest astronomical tide. These are the highest. So the difference between them is called as the highest tidal range, which will occur in a particular area. Like that, there are mean high water springs and so on. So when the tidal range, that means the difference between the mean difference between the mean low water during spring and mean high water during the spring is less than 2 meter, it is called as a microtide. When it is between 2 and 4 meter, it is called as a mesotide. And when it is greater than 4 meter, it is a macrotide. So as far as the Indian Ocean is concerned, you can see how the tidal variation is there. So if you go in the southern side of our country, Tamil Nadu, Kerala, and all these things, the tidal range is between 0 to 2. So the type of tides which do prevail, they are micro type of tides. If you come in Karnataka and Andhra Pradesh and some part of Orissa, you can see that the tidal range is varying between 2 and 4 meter. As far as Maharashtra is concerned, it is, and some part of Gujarat up to say Valsad and so. So the tidal range varies between 4 to 6 meters. So it is in the range of macro type of tides. This is mesotide, this is micro. And then there are extra large tides near Bhavnagar in Gujarat, where it is the second highest tide which occurs in the world is at Bhavnagar, where the tidal range is order of 12 meters or so. As far as Bay of Fundy in Canada is concerned, the tidal range is order about 23 meters or so. So in a tidal day of 24 hours, 50 minutes, the variation in the water level is about 23 meters. So naturally, as far as Gujarat, this Gulf of Khambat and Gulf of Kutch is concerned, there is a large variation in the tidal range. So naturally, the current strength, because of this flooding and ebbing, is quite strong. It has been observed that it is order of 3 to 4 meters per second. Now then there are tsunamis also. We have heard that on 26 December 2004, there was a tsunami in the Indian Ocean, where some portion of the land, that means the plateau of the Australian and Burma plate, it had gone down the Indian plate by about 15 meters or so over a distance of about 1,000 kilometers. So large wave is generated. So these tsunami waves, they are fast propagating waves, and these fast propagating waves, they travel at a speed of about speed of jet, maybe say 700 to 800 kilometers per hour. So whenever you are in deep sea, naturally the variation in the water level, or that means the wave height, is very less, say even 10 centimeters or so. So when the ships are plying in shallow water, then in deep water, they will not even feel that some wave is passing. But when these waves, they come towards the coastline, its wave height goes up to 30 meters, 40 meters or so. So this is one of the example of a Kachal island. So before 26 December 2004 tsunami, this was the actual photograph of a Kachal island in Andaman. And after the tsunami has passed, you can see that most of the portion is washed away. So tsunamis are more dangerous. And these tsunamis, they occur frequently in Pacific Ocean. Then there is a sediment transport that also we have seen. So these are the very important phenomena. So because of tsunamis, because of cyclonic conditions and so on, the thing is that hello, are you able to hear me? Hello?
Yes, sir, you're audible.
Yeah. So you can see that because of such conditions, the flooding will take place in the coastal cities. Then it will cause damages to the coastal protection works which are constructed. It causes capsizing of the ships at the harbor entrance. It causes a severe erosion in along the coastline. You can see the extent to which the coast is getting eroded. So these are very dangerous things. So despite these things, these things, severe damages to the properties and human life due to the dynamic behavior of ocean. Since ancient time, many countries in the world, they were adopting waterborne transport as the major mode of transport because it is the cheapest mode of transport. And about, I can say, 40% of the world population resides in coastal areas. So we have to be very careful while designing the coastal structures in coastal areas because they are subjected to such type of hostile environment. So as far as Indian Ocean is concerned, these are some of the shipping routes through which the ships they ply into the different areas, like into the Persian Gulf areas, then to the through the Gulf of Aden, through Iran and all these things. It goes into the Mediterranean Sea, that means towards Europe. Then on the east side through the Malacca Strait, you can pass through the Singapore, go to China, and again further if you go on this side, you can go into the Pacific Ocean. So these are the major sea routes in the Indian Ocean. And in order to serve the waterborne transport need of our country, we do have, I can say, 13 major ports. And in these ports, the ports in Gujarat, in Kandla, the port Kandla in Gujarat, in Maharashtra, there are two ports, Mumbai Port, Jain Port, in Kerala, Cochin Port, and in West Bengal, we do have Kolkata. So they are situated far inside from the open ocean. So the tidal phenomenon is more dominant in such cases. While rest of the ports, they are on the having their waterfront facilities exposed to the open ocean. So in such cases, the wave phenomenon is more dominant. And then in that case, you can see that the breakwater structures are essential to provide a tranquil condition inside the berth. So this is on the coastline of the India. So in order to protect the coastline, the sea walls are constructed. Then the berthing facilities are created, and these berthing facilities, they are protected with the help of breakwater structures to achieve calm conditions at the berth. Then the fisheries harbors are created to provide a berthing facility for the fishing vessels. Then oil jetties are constructed, and these are constructed and their alignment is made in such a fashion that irrespective of the phase of the tide, whether it is a flood tide or the ebb tide, the direction of the flow will be parallel to the berth, so that there will not be any extraneous forces acting on the mooring ropes on these ships, and it will have a trestle approach through which the pipes will be laid on top of which the pipes will be laid, and the oil will be taken towards the shoreline. Then the port, the breakwater structures, they are constructed to have a very good harbor facility. Here you can see a marina is there, then oil tanker has come here, then some small jetties are there, and so on. And naturally, the breakwaters are the structures which are constructed to protect these marine facilities. And out of the total cost of construction of any port development, about 30% of the cost is incurred in the construction of the breakwater structures. So these are the various types of harbor. Mumbai harbor is called as a natural harbor because this artificially developed landmass acts as some sort of a barrier for the waves coming from the southwest direction. And the port facilities are developed on the leeward side of it. So as far as the Mumbai area is concerned, the Bombay port is concerned, for them, they are having a closed docks and so on. Then there is an artificial port, what is called as at Paradip in Orissa. The entire land mass is excavated and is on the east coast. So there are two important directions through which the waves are coming. One is from the southwest direction, and another is from the northeast direction, because there are two monsoons on the east coast. So the two breakwaters are provided to achieve the tranquil condition inside the harbor. Then Cochin port is a estuarine port where the seawater is coming through the Cochin Gut location, and there are a number of rivers or the backwaters are there. They bring a lot of fresh water as well as the sediment into this area. So it's called as a estuarine port. And then there is another port, what is called as a New Mangalore port. And this New Mangalore port is provided with the breakwaters to achieve a calm condition inside the harbor. Then these are some of the components of the port. So this is called as the entrance channel through which the ships are coming. Approach channel, then there is an entrance channel here. When the ship starts entering inside the through the breakwaters, inside the breakwater section, then this is the location where the ship gets turned and then it goes towards the oil jetties or some container berths. So where the ship turns, then inner harbor area, then berths are there, wharves facilities are created, then jetties are constructed. Then the breakwater structures, you can see the big breakwaters are there. They are constructed to achieve calm condition here. Then a sand trap is there. Naturally, is on the east coast. So there is a lot of sand movement from the south towards the north. So once the breakwaters are constructed, the sand will get accumulated on the southern side, while on the northern side, there will be erosion. And then naturally the reclamation will be there for stacking of the metal which the ship had brought. So these are the major components of the port. So in order to finalize the alignment of port layouts, alignment of jetties, wharves to study the effect of reclamations on the surrounding, it is very essential that we should know the important phenomena which plays a very important role in the design of coastal projects. What are they? They are nothing but the gravity waves, tidal waves. If your ports are to be developed in a riverine area, then river flow is also important, and naturally the sediment which is there. So in coastal engineering, two types of wave phenomena are important. One is nothing but the gravity wave. Its period varies between, say, I can say from 1 second to 30 seconds. And another is nothing but a tidal wave. So its period varies from, say, 12 hours to 24 hours. So these are the two important phenomena which needs proper presentation which needs proper consideration while designing and planning the ports. So when the waves are coming at some angle, naturally it will have two components, one component parallel to the shore and another component perpendicular to the shore. So when it is perpendicular to the shore, the movement of the sand is called as onshore offshore. And when it is parallel to the shore, it is called the longshore transport. So these longshore transports which are there, so if you are planning any harbor facility inside, naturally when the structures are constructed to have a smooth movement of the ships into the harbor area and again into the ocean. So in such cases, because of this longshore transport, the sediment movement will be there. And on one side, the accretion will occur, while on the opposite side, the erosion will take place. Further to this, the movement of the sediment carrying water, when it starts entering into a dock area, it will get silted up at the dock entrance. Again, when the ships are entering through the navigational channel into the port area, and if there are cross current, then the captain has to see that if he has to take a ship here, he just simply cannot go here, but he has to go like this. So because of the current, the ship will get drifted here. Again, he has to bring it to the original position. So like that, he has to navigate his ship in such a fashion that it can go smoothly inside the harbor area. Then you can see the riverine flow. Many times in riverine flows, the flow is quite complex in nature, turbulent in nature. And then simulation of such complex flow with the help of mathematical model is very difficult. Then these are some of the examples how the coastal environment is there in the ocean, coastal areas. Waves are entering into the sea whenever there is a stormy condition. You can see here the waves are getting on top of this these breakwater structures which are constructed. It causes inundation of the harbor area. Then here you can see that overtopping causes excessive ship movement So when the waves gets overtopped, there will be a lot of movement to the ships. So we have to be very careful while designing the crest level or top level of these structures. Then it causes damages to the approach roads to the harbor areas. It causes loss of access to the harbors. It causes flooding over the roads, coastal cities, overtopping under extreme stormy conditions or due to storm surges, damages to the coastal properties, inundation of warehouses. Then you can see that there was a bund which was constructed and the port facility was on this side, but because of the rise in mean sea level and because of it causes breaching of this bund and the water starts entering into the harbor area. Damages to the breakwater structures, impact of cyclonic conditions. I will just show you what had happened. As far as Mumbai, you can see here, there is a lot of overtopping of waves near a gateway of India. These are some of the pictures on 26 July 2005, when there was a heavy rainfall of 1,000 millimeters in one day. At the same time, there was a high tide in the Arabian Sea. So the water does not go into the ocean. As such, it causes jamming of the railway lines, the roads, jamming of the airport, Bombay airport, and so on. Impact of such cyclonic conditions, tsunamis and all these things on the coast, you can see how they are dangerous. On the port structures also you can see. So development in coastal area has to be a sustainable development, and how it can be achieved. So development in coastal area is sustainable when harbors constructed keeps the adjacent coastline stable. So you have to carry out a lot of investigations, you have to carry out field investigations, you have to carry out the modeling, because after all we are playing with the nature. That too again, that type of nature which constantly changes its magnitude, not only with respect to time, but with respect to space also. So how to achieve such development without harming the nature's balance? So CWPRS is a premier hydraulic research institute of our country, was established in 1916. And for past 106 years, this research institute is serving our country for carrying out all sorts of a development which are related to the water sector. So we do have a number of disciplines like river engineering and river and reservoir systems, that means dams and hydraulic structures, coastal and offshore structures, foundations, and so on. So among that, coastal and offshore structure is one of the important branch. So ocean phenomenon is complex. Tidal phenomenon is unsteady, which varies in space and time. So there is a continuous change in the direction of flow over a period of tide. Waves in the ocean, they are random in nature. That means the height period and its direction changes continuously. Plus, it goes under different processes like refraction, diffraction, reflection, transmissions, and so on. Sediment transport is again more complex, as different type of sediments, they moves, settles into the seabed, again is brought into the resuspension with the flow of tides and waves. Then wave structure interaction is also an complex, because when the random waves they hit a particular structure, which is a multi-layered porous structure, what sort of a force will be acting on top of it? Till today, there is no mathematical model which has been developed in the world which can truly simulates this wave structure interaction. So till today, the people has to rely on the physical model. Then these are some of the coastal and optioning capabilities of CWPRS: optimization of port layouts, storm surge computations, wave windcasting, extreme value predictions, design of marine structures, ship motion and maneuvering problems, dredging and disposal, coastal processes, evolution of shoreline, coastal erosion, protection, stability of coastal inlets, environmental and water quality studies, geophysical investigations. Naturally, for doing all these things, you require a lot of field data, as well as the application of remote sensing to solve the coastal problems. So development in the coastal region requires application of hydraulic modeling because the processes are quite complex in nature. It varies in space and time continuously. So understanding the ocean phenomena is very important. So what are the physical processes which are taking place? It should be known. So it is very essential that the modeling is required. So in case of port planning, now we will see that there is oceanographic, that means wave climate to assess the tranquility inside the harbor. Hydromorphology, study of tides and currents for finalizing the port layouts, then estimation of siltation in channels, berth pockets, and so on. Then hydronautics related to ship simulation studies, design of marine structures like quays, jetties, breakwater structures, and so on. So the development of well-planned coastal cities which can withstand dynamic impact of coastal phenomena needs careful consideration of understanding of various coastal processes and can be achieved only with the help of application of hydraulic modeling. So hydraulic modeling is very essential. So just now we have seen this, that tidal phenomena, which is more important as far as these ports which are situated inside the estuaries or creek regions. So this is an example of a Mumbai port where the tidal phenomenon is more dominant. Even though the waves are coming during southwest monsoon, this artificial developed landmass protects these port structures. And as far as the Jawaharlal Nehru port is concerned, is situated far inside from the open ocean. So the waves do not have any impact on the ships which are berthed in this. So tidal phenomenon is more important. So this is Mumbai port, JN port. This width is observed about 10 kilometers, and the water spreads far inside up to the Thane city, 30 to 40 kilometers. So these are some of the salient features of the Mumbai. So is situated on the west coast of India. Macro semi-diurnal tides, maximum tide range is about 5 meters. It has a very ultra-wide estuarine entrance of 10 kilometers, and the tidal water spreads far inside 30 to 40 kilometers. So you can see here, water spreads right up to Thana city. Then there are a number of creeks which are meeting in this Thane Creek. There is a Panvel Creek, Dhawa Creek, Karanja Creek, Dharamtar Creek. So many creeks and the riverine areas they are meeting in this area. So the flow is quite complex in this region. As well as southwest monsoon is also more dominant. So tide dominated flow moves in and out of estuary with exchange of large water mass. So this is what we have seen just now, how the study is very much essential to estimate the siltations in the dredged areas and the berth pockets for which the tidal modeling is essential. Similarly, there are number of ports where the wave phenomenon is more dominant, like Marmagova port, Mangalore port, Tuticorin, Chennai, Ennore, Visakhapatnam, Paradip, etc. So in case of the ports which are facing the open ocean, naturally the wave phenomenon is more dominant, and it is very essential that you should know what are the tranquil conditions inside the harbor. So for that, the wave modeling is essential. So to protect the coast, you can see the fury of ocean waves. The waves are breaking on the coastal structures, formation of eddies and vortices in the navigational channel, then flow separation, turbulent flow, simulation of such phenomena like wave breaking, turbulent flow in rivers where there is an entrainment, air entrainment is there, tidal bore. So such flow phenomena are very difficult So such flow phenomena are very difficult to be simulated in by numerical techniques. So how to evolve a layout and design of coastal hydraulic structures? By understanding the physics behind various hydromorphodynamic processes and knowledge of hydraulics with the help of pure theoretical approach, but however this theoretical approach is useful for laminar flows only. Empirical methods based on correlation between observed variables like water depth, velocity, acceleration, which are affecting a particular physical system, should only be used under similar circumstances under which data was collected for deriving that particular empirical relations. So suppose, for example, some formula is developed to study or to estimate the siltation in Mumbai region based on some flow conditions which are prevailing in Mumbai region, say Thane Creek region, then that formula which has been developed for the Mumbai region cannot be applied for Cochin. It cannot be applied for Paradip areas. So empirical methods, they do have a lot of limitations. Semi-empirical methods are the mathematical formulations which are based on theoretical concepts supported by suitably designed experiments based on dimensional analysis. So students will definitely understand what are dimensional analysis. So in case of dimensional analysis, the number of separate variables involved in a particular type of physical system, they are rearranged into smaller number of non-dimensional groups. Say ratio of inertial forces to gravity forces, ratio of inertial forces to viscous forces, like that. So the arrangement of variables in each group is generally chosen so that each group has some physical significance. Say main force component on fluid are either due to viscosity, that means Reynolds number, gravity, then Froude's number, pressure, surface tension, etc. Then we can have a physical models also. We can have mathematical models also. So why modeling is essential? Physical processes in coastal zone are dynamic and act simultaneously. So empirical methods alone cannot give the best engineering solution. Effect of proposed development on surrounding area cannot be predicted in advance without simulating the complex flow phenomena. So if you are not able to simulate the complex flow phenomena, whatever the development you are proposing in a particular area, what is its impact on the surrounding area? It cannot be understood. Analytical methods alone cannot give the solution to coastal problems due to complexes in physical processes. Site-specific field data alone cannot evolve morphological changes resulting from development under consideration. So just by collecting field data, you cannot understand what sort of changes will occur in a nearby area because of the development in that region. So whether there will be increase in sedimentation or what.
Hello?
Can you hear me?
Yes, now we can hear you, sir.
Yeah, I think there is some problem with the system. I have to continuously move this up and down to read what is there on the.
So you are audible. Just for few seconds, you were not audible. You are audible now.
Okay. So the study of hydraulics in scientific manner was done by Leonardo da Vinci in 1500 itself. He says that when we are dealing with water, first experiment and then use the judgment. That what he talked in 1500. So the first physical model was developed by John Smeaton in 1752. So since ancient time, physical models are used in reverse to demonstrate the correctness of regulation measures, like say dikes burns on the surrounding area by Lewis in 1875. Reynolds had done the first experiment on a movable bed model for River Mersey with sand as a bed material in 1885. Then Dr. Dalrymper from University of Delaware, he says that in 1985, physical models constructed and operated at a reduced scale offer an alternative for examining coastal phenomena that are beyond our analytical scale. So he is again emphasizing that the physical models are essential. So hydraulic model includes use of scale models for replicating the flow and fluid transport processes in diverse natural flow system and for evaluating the performance of hydraulic structures and hydraulic machines. So CWPRS is not an exception to this and is being using the physical model since 1950 to simulate the ocean phenomena such as tides, waves for finalizing the layouts of harbors and port. So this is a view of a old Mumbai port model developed at CWPRS in 1950, and is basic, as I told you, that the tidal phenomenon is more dominant. It's a tidal model, and it was constructed in 1950 with a horizontal scale of 1 in 1000 and vertical scale of 100. So these are the various tools with the help of which we can solve the coastal problems. That means we can finalize the port layouts. We can study what should be the cross section of a breakwater structure so that it can withstand the wave forces which are acting on that structure. So there are physical models, like say wave models or tidal models. Then nowadays high-speed computing facilities are available. So now almost all the physical models except few phenomena which till today cannot be simulated using mathematical models, the physical models are being used. And naturally the wavefilm facility is still used or is the only way to assess the hydraulic stability of marine structure. Then in addition to that, we do have dust studies, remote sensing, and so on. So physical hydraulic model. What is a physical model? It is a physical system which is reproduced naturally. In case of coastal engineering, the model which is having a smaller size compared to that of the prototype. So it is a physical system reproduced so that the major dominant forces which are acting on the system, that means on the water body, are reproduced in the model in correct proportion to the actual physical system. So what sort of forces which are acting on a water body in the ocean, they are properly reproduced in a physical model, or it is called as a precision device which is used to predict the behavior of physical phenomena. So that's why physical model is called as a nature in miniature. The physical model is also used when flow conditions in natural phenomena are not amenable to mathematical analysis. Say, for example, wave breaking. For example, if wave structure interaction, flow separation, such phenomena still today are not possible to be studied using a mathematical model. Their physical model are very important. So what is a physical model? It is a scaled representation of hydraulic flow phenomena and cannot be disassociated from basic theory of fluids. So you should know what are the basic theories of fluid. In coastal engineering, a physical hydraulic model is always smaller than prototype. So what are the goals in conducting physical model? Seek the qualitative insight into such a phenomena which are not yet understood. Say, for example, turbulence which is created due to wave breaking. Obtain the measurements in a model to verify or disapprove the theoretical results. Say, for example, non-linear interaction of tidal flow with the riverine flow. And obtain the measurements for phenomena which are so complicated that so far they have not been accessible for theoretical approaches. Say, for example, stability of rubble mount breakwaters. So there are goal related to finalize the alignment of the berths, alignment of the diversion burns, the flows which are taking place. So they are goal related, and all these physical models, they are rigid bed models. Similarly, there are some models which are design related. Say, for example, to assess the hydraulic stability of breakwaters, groins. So they are related to design of the marine structure. And there are some mobile bed. Here we have seen the fixed bed model, like that there are mobile bed model also. Say, for example, to study the beach profile, dune erosion, score at the bottom of coastal structures. So you can see. So using the piles are there and the waves are generated, and this is a mobile bed model. So you can see how the score is taking place. You can see the formation of ripples and all these things. So from that you can estimate how much amount of scoring must have taken. Necessity of physical model in design of marine structures. Phenomena such as wave breaking, wave structure interaction, effect of porosity on wave run-up. That means when the wave hits, it goes up. So how much amount of energy is absorbed inside the structure, which is a multi-layered structure, is not still possible by using analytical methods or by mathematical models. So their physical model is required. Simulation of eddy formation, flow separation is again a very important thing. It cannot be done using mathematical model unless you do have a 3D model, and 3D model requires a large computers. Flow separation, horizontal entrainment, simulation of horizontal entrainment is very difficult in mathematical model and could not be visualized also properly. So it can be visualized properly on a physical model. Then field data collection alone cannot be relied upon, as it will not be possible to determine what will be the impact of deepening of the main channel, or maybe say dredged area, or maybe the shape of the reclamations on this surrounding area. So for that purpose, the physical model still plays a very important role. So you can see, because of reclamation, large eddies are getting formed. So just by collecting the field data, you cannot come to know what will be the impact of that development of the surrounding. Then assessing the wave tranquility inside the harbors. So what should be the alignment of the breakwater when the waves are coming, how the waves will get. Here you can see very nicely. The waves are coming and they are getting diffracted. These are the wave crests you can see. And in the sand trap area, a calm condition can be achieved. So what should be the length of this breakwater? Optimal length of the breakwater, so that the overall cost of construction of breakwater can be reduced. So physical model plays a very important role. So fundamentals of fluid flow. Fluid is expressed by Newton's law of motion and conservation of mass and energy or momentum. So conservation of mass, everybody is known the continuity equation when the fluid is incompressible. We know that the fluid what we are using in physical model here is nothing but the water. So water is incompressible. So this is a continuity equation which is valid. Then the conservation of momentum, that means Navier-Stokes equation. It consists of inertia and the external pressure forces on acting on those water body. That is pressure force, viscous force, and the body forces. So the inertial forces are equated to the pressure force, the gravity force, viscous force, turbulent force, surface tension, and compressibility. So what are the important terms in the modeling? Prototype. Prototype is nothing but the situation which is to be modeled, either of same size or reduced scale. Scale, constant of proportions of measurable characteristics between the model and prototype. That is what we call as scale. Scale may be 1:50, 1:100, 1:20, like that. That means 1 meter in model corresponds to 20 meter in prototype. Similitude, the mathematical condition that must be made by these scale ratios. Suppose if I select a scale of 1:30, then what are the mathematical conditions which must be made by that scale ratios between prototype and model is called as a similitude. Similarity means a condition that exists when the model gives similar response as that of the prototype, even if the model is not in strict similitude. No, in any model, we are not able to reproduce the exact simulation of all forces which are acting at prototype, they are not properly simulated in the model. So there are some limitations of the modeling also. But when the model starts giving similar response as that of the prototype, we can say that there is a similarity exists. Then scale effects, difference between the prototype and model response that arise from inability to simulate all relevant forces in a model at proper scale dictated by scaling criteria. Now, what happens that many times if you want to simulate the tidal flow, naturally you have to simulate so many hundreds or thousand square kilometers of area in a model with some scale, maybe say scale of 1 in 1000 horizontal and 1 in 100 vertical. So there is a distortion of 10. So there are some scale effects. Then laboratory effects are also there. Now, what happens that now if I am simulating some tidal flow in a Bombay model at CWPRS, whatever the wind which is blowing in a Thane Creek at a particular time in Bombay, I cannot simulate that wind here in a Bombay model. So there are some laboratory effects also. Then hybrid modeling, results from the one model, say maybe say from physical model, is used to provide as an input to another model. It's called as a hybrid modeling. Then principles of similitude. The practical application of similitude in hydraulic scale model testing is based on understanding the fact that there is not complete similitude. Means I cannot simulate all the forces, but rather several imperfect similitudes which can be exploited. The basis of all physical modeling is the idea that the model behaves in a manner similar to prototype it is intended to match. A proper validated model can be used to predict prototype conditions. So validation of the model is must. So what are the concepts of similitude? Ideally speaking, a properly designed laboratory model should behave in all respect like a controlled version of a prototype. That means it is like a controlled version of a Mumbai harbor in a physical model of Mumbai port available at CWPRS. In fluid flow models, such behavior includes velocities, acceleration, water levels, mass transport, the resultant forces which that fluid is exerting. Then model similitude can be achieved by different ways, like calibration of a model by carrying differential equations, dimensional analysis, and scale saving. We will not go into the details of all these things. Practical aspects of similitude. Being known that achieving complete similitude of all forces ratio are constant and equal is impossible except prototype scale. That means what? In most problems, a combination of experience and engineering sense helps to choose the ratios that need to be simulated. So role of a modeler, I am a question engineer, I am a modeler. So what is the role of model engineer is to justify the extent of disagreement from complete similitude. Suppose if I am simulating some particular phenomenon in the model and is 95% matching with that at the with that of the prototype condition, then I can say that my model is giving 95% agreement. That means only 5% disagreement. And whether that 5% disagreement is going to cause any severe effect on the flow phenomenon which may take place at site. So that sort of a judgment an engineer should have, and that depends on the experience you do have and your technical abilities. And when possible, make theoretical corrections to complete the similarities. So model engineer has to be aware of forces that are negligible in prototype but have considerable influence in model. So for example, bottom roughness. So suppose if my model is distorted and if the distortion is very high, then the friction in the model, which will be much more higher as compared to the friction which will be there at site. So modeler has to consider these effects. So hydraulic criteria. Many major flow problems in coastal ring can be simplified into two major forces which dominate the flow, and you can make other forces negligible. So other forces may be say within that 5%. So inertial forces are always present in the flow problems. and they are to be balanced by the other forces. So inertial force is all very important. So inertial forces, gravity forces, and viscous forces, they are very important. So the inertial forces are equated with that of pressure force, gravity force, viscous force, turbulence, surface tension, and compression or compressibility. So when we consider that is a ratio of inertia to gravity, it is called as a Froude number. So when it is a ratio of inertia forces to viscous forces, it is called as a Reynolds number. So like that, there are various forces which we have to take into account. So when I'm taking water, the fluid is incompressible, so I should not consider Fc force. Now, if the flow is turbulent in nature, then surface tension will not be there. It can be removed. If my bottom surface is impermeable and the area what you are simulating in model is very small compared to the large domain, then you can eliminate the pressure force which is because of the atmospheric pressure. Then turbulent forces can be also removed if my flow is a tidal flow, or wherever there is a vertical variation in the velocity is not significant. So hydraulic model works on the laws of similarity, that is nothing but the geometric similarity, kinematic similarity, and Newton's laws of motion. So these are the three important things which are very essential in case of hydraulic modeling. Geometrically similar, that means whatever the shape and size of a prototype condition is simulated in model with the same scale with some scale ratio. Say 1:30, that means 30 meters on ground corresponds to 1 meter in model. Kinematic similarity means similarity of motion of a fluid in prototype and in model. And Newton's law of motion, that means whenever we are dealing with the hydraulic stability of marine structures, then forces will come into picture. So geometric similarity, that means this is a prototype, this is a model. When kinematic similarity, the flow which is moving around a particular structure in proto and in the model, whether they are behaving in similar fashion or not. And then the computation of forces, what is called as a dynamic similarity. So as far as coastal engineering is concerned, there are two important phenomena. I have told you they are nothing but the waves and the tides. So CWPRS do have permanent physical models for the port facilities where the flow wave phenomenon is dominant, as well as do have a permanent models for the ports where the tidal phenomenon is dominant. Say, for example, the Mumbai port model and a Marma-Goa port model. Similar to that, in wave models, we do have two different types of things. One is called as a wave basin, which is used to study the different types of small fisheries harbor. So, like that, wherever some new project is coming up, some new fisheries harbor is coming up. So, in a wave basin model, you can lay the bathymetry survey, that means the bed contours and the layout of that fishing harbor, and you can study how the waves are passing and what sort of wave conditions are shown. While Paradip port model is a permanent model where you can study only the wave phenomena related to Paradip port area. So in case of wave basin, we do have a random seawave generating facility, while in case of Paradip model, we do have mono. So these are some of the basic things. I will not go into the details because they are available there in the books, like Froude's law. Then based on the Froude's law, which is the ratio of inertial forces to the gravity forces, what is the velocity scale? So suppose if my model scale is 1:36, that means 36 meters on ground corresponds to 1 meter in model. So square root of 36 means what? 6. So if the velocity is there at prototype is 6 meter per second, in model it will be 1 meter per second. Like that, time scale is also square root of your model scale. So square root of 36 is say 6. So if the stormy condition is there at site for 6 hours, then you should, to simulate that stormy condition in model, you should run the model for 1 hour. Then they are used, wave phenomenon is useful, as I told you, to assess the wave tranquility inside the harbor as well as stability of marine structures. So case study, assessment of wave tranquility for development of oil jetty. So Paradip port, one of the major port of India, situated on the east coast in the state of Orissa, were having two breakwater structures, and they were proposing to have a new facility on the leeward side of this north breakwater, and they would like to know, they do have existing facilities like central dock, then eastern dock, and the channel was maintained to a depth of 14 meter also. And then they were proposing to have a proposed oil jetty on the lee side of north breakwater, and a new dock to be was proposed on this side. So whether if you develop this oil jetty here, whether for how many days in a year you will get a tranquil condition so that the ships can be berthed here. So those studies like that type of studies were referred. So this is a Mahanadi river which meets the Bay of Bengal. Is having a 6-kilometer long seawall, and this port was established in 1966, and these studies were referred to CWPRS in 1997. So they were interested in knowing for an oil tanker of 250,000 deadweight tonnage, what will be the flow conditions, what will be the wave conditions in the navigation channel, turning circle on the lee side of north breakwater, as well as in the sand trap also. So for that purpose, lot of investigations were required, like that. You should know what are the wave climate in deep sea. You know what are the wave climate in intermediate depth, then water depths, tidal range, bathymetry, then type of waves you are generating, area to be simulated, whether sufficient water supply is available or not, what sort of a data acquisition system, whether it is computerized or strip chart recorder type, for how much duration the study is to be carried out, and so on. So from deep sea, the wave transformation was carried out, and you can see here. So this is a wave rose diagram. So from these directions, the waves are coming from deep sea off Paradip. So when these waves get transformed because of the refraction and shoaling, at a particular point very close to the port harbor, what are the dominant directions? So we found that the east, southeast, south, and south southwest, these are the dominant directions after carrying out the wave transformation studies. So for this we have used a mathematical model. So like that you can have plotting of refraction diagrams also. So this is a layout. This is the east southeast direction where the waveboard is there. This is the south direction where the other waveboard is there. This is a main navigation channel through which the ships comes. So these are the docks existing. A new dock is proposed here, and oil jetty is proposed here, and this is a sand trap. So the studies were carried out. You can see the view of a physical model. It was constructed with a scale of 1:125, and it is a rigid bed model. Is having a size of 56 meter by 53 meter, and these are the various scale ratios you can see here. So here you can see how the waves are generated from the south direction. They propagate, they comes in, and this is a sand trap area. This is a sand trap area, and this is that oil jetty where what are the wave conditions. So for different conditions, different waveguides, different periods, from two different directions, the model was run. A physical model was run. So if the wave height at the board is 2.5 meter, which we have derived it from the wave transformation studies, from deep water to intermediate water depth in a 14-meter depth, how the wave propagates. So you can see the navigation channel, the wave height gets substantially reduced. And at the berth, it is about 0.21 to 0.3 meter. So which is much, much less compared to the permissible tranquility limit for the 250,000 container carriers, 250,000 very large crude carriers are concerned. So for the waves coming from east southeast direction, there is no problem. But in the sand trap, you can see the waves are about 2 meters. So the dredger cannot work in this area, because for the dredger to operate, it requires a tranquil limit of 0.5 meter. Similarly, from south direction, the waves of about a 4 meter, 10 second or 8 second period, they are coming. And you can see here at the oil jetty, the waves of the order of 0.6 to 0.63 meter are there. While in the sand trap, they are about 3.5 meter. So as far as the waves coming from south direction is concerned, there is no problem at the oil jetty, but at sand trap, there is a problem. Dredger cannot work. So breakwater was suggested of about 1 kilometer length. And that breakwater was again modified by CWPS and a new alignment and layout was evolved. And the studies were carried out. So with this breakwater, where the waves are coming from this direction, the waves of about 0.21 to 0.26 meter are there in the sand trap. So dredger can easily operate. While inside it is still further less compared to the earlier one. Similarly, from the south direction, now in this area it is about 0.69 meter. But at this end, it is about 2.2. So the dredger cannot work here during southwest monsoon. That's why CWPRS has modified this shape and alignment of the breakwater. And here you can see that the wave heights are about 0.46 and 0.49 meter. So it is less than 0.5 meter. As well as inside the near to the oil jetty are about 0.12 to 0.25 meters. So still they are less. Similarly, from the south side, you can see about 0.6 meter in the sand trap. And there is no problem here. So the studies were carried out on a physical model, and you can see that under the existing condition, oil jetty, yes, it can operate for 355 days. In the sand trap, the dredger can operate for 80 days. While the alignment of the breakwater suggested by Paradip Port, there is no problem for oil jetty, but in sand trap, the dredger can work only for 200 days. And what recommended by CWPRS with its alignment and layout finalized, you can enhance the working days of a dredger from 200 to 265. So earlier they were able to operate only for 80 days. Now they are able to operate for 265 days. So like that, physical modeling is very much useful. Like that, for another wave basin, the model studies were carried out for a small fishing harbor where the wave basin is available. And these are some of the salient features of the wave basin facility which is there available at CWPRS. You can generate maximum 17 centimeter wave height. And the significant wave height corresponding to the maximum wave height is about 10 centimeter. I hope that Dr. J.D. Agarwal must have told you some idea about in the random waves that what is the ratio of H max to significant wave height and so on. So normally you will find that in the ocean, when you consider different type of spectrum, say Pearson Moscovitch spectrum, then the ratio of H max to HS is about 1.67. So that's why you can see here, you can generate 10 centimeter. 10 centimeter multiplied by 50. So that will give you the wave height in prototype. So for Pumpuar, the studies were carried out using both mathematical model for the development of a fishing harbor in Tamil Nadu. And with the mathematical model, we found that with this south breakwater about 1100 meters and a north breakwater about 390 meter, it can operate for about 325 days. So there is a loss of operational days by 40 days. So same thing was studied on a physical model also with a spectrum, because that was a spectrum like Scott spectrum which was prevailing at Tamil Nadu coast. And you can find here that there is no loss of working days. So it gives us some sort of a fine refinement over that of the mathematical model. So till today, and the length of the breakwater from 1100 meter has been reduced to 1085. While the north breakwater, earlier it was 390 meter, which was studied using mathematical model. Now we can reduce it to 300 meter or so. So still with this, you are able to operate it. There is no loss of working days and the reduction in the length of the breakwater also. So you can see how the layout recommended was constructed at site and it is functioning properly. Similarly, there is a tidal model So the application of tidal model or a physical tidal model is to finalize the alignment of navigational channel based on flow direction for smooth entry and exit of ships, optimize the berth location, their alignment with respect to the tidal currents, finalization of port layout, and evolve likely regions of siltation. What are the impact of the proposed structures or reclamations on the surrounding area? Optimize the channel dimensions and from the navigational aspects, optimization and orientation of the guide bands, study of thermal dispersions, and so on. So tidal models are the models which requires a large area, and naturally whenever you have to simulate a very large area, if you construct a geometrically similar model, then the water requirement will be also too high. Now, say for example, the Bombay model, which is available at CWPRS, it covers an area of about 180 meter, or I can say 150 meter by 80 meter, which covers an area of about 2000 square kilometer at prototype. And out of 2000 square kilometers, 70 meter by 45 meter area of the Thane Creek is covered with the help of a shade. So it considers an area of about 500 square kilometer. So distortion is essential because the carrying out distortion doesn't significantly affects the flow conditions in model, which we can compare it with that of the site. So tidal models are distorted to avoid capillary effects in model, to avoid too long models, to have sufficient depth in motors, depth of water in model so that the instrument can be dipped and you can measure the velocities and water levels. And the time scale should be such that, that means your distortion should be such that the time period is not too long. That means I have to carry out the measurement for one tidal cycle over a period of say 1 hour. And if you want to repeat it, it will be too costly affair. So you have to have some sort of a judiciary selection of a model scale so that the entire model operation will not be also too costly, as well as it will not cause inaccuracy in the measurement, and the flow conditions are properly simulated so that the results which are obtained from a physical model can be directly implemented at site. So these are some of the equations. So velocity scale in case of distorted model, as I told you, is a distorted model, say 1:1000 to 1:100. Then velocity scale will be the square root of the depth scale, that means square root of 100. In case of geometrically similar model, there is only one scale, say 1:40. So it will be nothing but the square root of the model scale. But in case of distorted model, there are two dimensions, the horizontal dimension as well as the vertical dimension, while the time scale is nothing but the, so this is based on the Froude's law similarity. So you can compute for different scales, what will be the velocity scales, time scales, discharge scales, force scales, and so on. So these are some of the things which are theoretical, so I will try to skip it here. So normally the distortion in case of tidal model is allowed up to 10 only. That means if my model scale is 1000 horizontal and 100 vertical, the distortion ratio is 10. But if my distortion goes beyond 10, naturally the frictional forces, they come or plays a dominant role in a model, and then the flows which are turbulent in nature becomes laminar in the model. So that indicates that your flow simulation is not proper. So normally the distortion is restricted between 5 and 10. So the earlier model of Mumbai model, which was available at CWPRS, was with a horizontal scale of 1000 and a vertical scale of 100. So the distortion was 10. So these are some of the Manning's coefficients. So according to that, you have to reproduce a smooth bed plaster depending upon the type of soil which do prevail at site and what type of bed you are simulating in model. So using Manning's criteria, you can decide what should be your model scale, so that the friction can be simulated properly. So when the vertical exaggeration is greater than 10, in the model, there is too much of frictions and it disturbs the local flow pattern. That's why the vertical exaggeration is kept less than 10. So the new Bombay model, which was constructed at CWPRS, was constructed with a different scale. Horizontal scale was 400 and vertical scale of 80. So the distortion has been reduced from 10 to 5. So I will skip this one. So this is the old Mumbai model, was used from 1956 to 83 with this scale. This is a new Bombay model with a horizontal scale of 1 in 480. Is equipped with the automatic tide generating system, is a fully controlled automatic tide generating system. So this is a gateway of India. This is an inner view of a physical model. So this is a main navigation channel. It gets bifurcated to Bombay port. So Bombay port area is here. Indira Dock channel, then it further goes here, it goes to the Jawaharlal Nehru port. So it's a basically tidal model. So these are the various facilities which are available here. And you can, based on the distorted scale and as per the Froude's law, you can say that my model scale becomes 1 second to 44.72. That means if for 44.72 second corresponds to 1 second in model, my tidal cycle is of 12 hours, 25 minutes. So half of it will be flood tide, half of it 12 hours 25 minutes will be ebb tide. That means flood tide will be 6 hours 12.5 minutes. So with this model scale, it becomes 8 minutes 20 seconds of flood and 8 minutes 20 seconds of ebb. So my total one tidal cycle is equal to 16 minutes 40 seconds, which corresponds to 12 hours and 25 minutes of duration at prototype. So the same phenomenon I can study within just 16 minutes 40 seconds in model. So these are the, in olden days, this strip chart recorder was used and the discharge measurements were carried out with the help of V notches. Nowadays, the sophisticated equipments are available to measure the water level sensors called as a radar sensors. So they are non-contact type of sensors with an accuracy of 1 millimeter, and SCADA system is there to measure the discharges. So rather than using V notches, we do have a computer controlled discharge systems which can simulate the hydrographs also. Here you can see the facility which is available at CWPRS or Mumbai port model. So from the tank, the water is taken into supply channel. The water level is measured with the help of sensor, and with the help of computer, you can generate the tides. You can see the tides in deeper part of the ocean. It use the signal to stepper motor, and this stepper motor with the help of shaft moves. With the help of these shafts, it moves the gates which are there. So these are the gates you can see here. So tidal model is useful to study at what time the ship should start coming in, to finalize the alignment of channel and its dimension also. It is used to study the flow conditions because of the proposed developments, to finalize the alignment of the jetties where there is a confluence of two channel. You can see the actual one it's constructed at site based on the recommendations given by CWPRS. Then determine the flow conditions to determine the siltation, likely siltation in the area. Finalizing the alignment of bund so that the flow conditions near the proposed jetty location will be not get affected. So this is a case where the Jawaharlal Nehru port is here. There is a one creek called as a Dawa Creek, which is coming from here. There is an Elephant Island, and the main flow is like this. So the creek is meeting, Dawa Creek is meeting at right angle to the main channel flow. So they were proposing some 330-meter long container terminal. So for this container terminal, you have to divert this flow which is coming during ebb tide and going inside during flood tide in such a fashion that it will not cause any problem to the ship visibly berth here. So physical model studies were carried out, and whatever the ships they will be bringing the container, it needs to be stacked. So what will be the impact of this shape of the stackyard on the flow conditions in this area? They were studied. The complexity is that here the bed levels are 1 meter below the lowest low water level, while in the main channel they are 14 meters. So there is a very steep gradient of the bed contours in this area, and there is a lot of turbulence which is getting generated. So simulation of such flow, complex flow phenomenon with the help of mathematical model is very difficult. So that's why it was studied on a physical model. So this is some of the examples of flow conditions, that means the current, speed and direction. And for different conditions, the model was studied with triangular shape of reclamation, with the modified shape of reclamations and so on in Nava Creek. These are the flow conditions and the measurements were carried out. So during flood tide, when the water starts coming in, you can see this is the existing terminal. This is a earlier bund which was there. And during the flood tide, the water goes inside into the Nava Creek. While during ebb tides, during initial hours of ebb, the flow comes very fast. So this is the flow which is coming fast out. So the Elephanta side is on this side, Nava Creek is on this. So the flow measurements were made at the entrance location, and based on that, so the recommendations were given, and it was recommended that this bund, which is to be, this is the Nava Creek side, this is a terminal construction going on 330-meter long, and with the help of this guide bund, the flow which is entering into the creek and going out was diverted, so that it will not have any impact on the ship which will be berthed here. So using physical model, the studies were carried out, and you can see the ships are nicely berthed at this location, are not creating any problem for the ships. So this is how a physical model is useful in finalizing the orientations and the angle of the guide bund so that the facilities can be created. Then near the coast, now there is a erosion. Now we are moving from wave model to tidal model, and from tidal model we are going now to the coastal structures. Now this is a Marvante in Karnataka. So you can see the type of erosion here. So coastal erosion is a menace faced by all maritime countries in the world. And because of the climate change and all these things, you will find that bigger and bigger waves, they are getting generated. And when they are approaching towards the coastline, you can see a lot of erosion is taking place. And this erosion will get aggravated. So on one side, there is the Arabian Sea. On the leeward side of this area, there was a river is there. So only small portion of the National Highway number 17 was remained intact. So to keep it intact and avoid the erosion, the studies were carried out at CWPRS. Similarly, Swaminarayan Temple in Gujarat, there is a lot of erosion, you can see here. So these are some of the photographs where the erosion is taking place, different types of erosions. You can see cliff type of erosion. The erosion also occurs because of the construction of the breakwater. So on one side, there is accretion. So there is accretion on one side and the erosion on the opposite side, on the other side. So I can say that study of wave mechanics is important to protect the coastline against the attack of waves by evolving site-specific engineering measures for coastal protection and to design the hydraulic stability of marine structures. So hydraulic stability can be studied in a wave flume facility under the attack of either monochromatic waves or random waves. So there are structures are classified as rigid structures, semi-rigid structures or composite structures like caissons resting on the rubble base, and the flexible rubble mount type of structures. So you can see, so these are the flexible rubble mount structure consisting of different type of stones having different weights. So for that, it is very essential that you should know what sort of a wave data is required, say observed data, instrumentally measured data. And hindcast data means you have to carry out the analysis of the cyclones which has occurred in last 20-30 years. And after carrying out that analysis of cyclones, you can determine what will be the wave conditions that storm might have generated. And then you can put that data into an extreme value analysis, and you can determine the design wave conditions. So visually measured wave height with the help of ships. It is important for captain of a ship to report it to the nearest port. The significant wave height, zero crossing periods, its direction also, and the measured instrumentally recorded data is also there. It is much more accurate compared to that of visually observed. So as the waves enter the shallow coastal water, due to the effect of refraction and shoaling, the waves picks up to such an extent that they cannot sustain and consequently breaks. So wave breaking criteria is considered as an important criteria in finalizing the design of marine structures. So normally when the bed slopes are very flat, then in that case the ratio of wave height to the water depth in case of flat seabed slopes, that ratio is about 0.78. So this is why we have seen in the morning just now. Then wave data analysis is carried out. There are two types of wave data analysis required. So if you are dealing with monochromatic waves or regular waves, where the wave breakings are concerned, they are either depth limited or steepness controlled. And various theories, wave theories are available. So using those various wave theories, you can generate such waves in a model. While whenever we are designing the marine structures like breakwaters, which are situated in relatively deep water, the probabilistic analysis is required either by statistical methods or by spectral methods. So these are highly mathematical techniques which needs to be understood, and it's not that easy that one can understand within one lecture. So you have to spend years of time in learning all these things. So I am, based on my experience for last 29 years at CWPRS, I got an opportunity to work in the various fields of questionnaire. I'm trying to deliver the knowledge what I've gained through this lecture to the participants. So monochromatic waves. So there are some charts are given in the shore protection manual published by US Army Corps of Engineers, or nowadays there are CEM is there, coastal engineering manual is there. So if you know the water depth and the wave period, take a ratio of d by gt square with that of h by gt square, that means the wave height and the period square, you can determine what wave theory is to be used. And for structures which are situated in shallow water, normally they are tested under the attack of breaking waves. And with these various wave theories, you can determine what should be the crest level of your structure. Then a random wave data analysis, it is not that easy to understand, because you have to do either fast Fourier transform analysis, spectral analysis, or by means of statistical methods. And then you have to plot a spectrum. So understanding of random waves itself is a big thing, and it requires so many hours of dedicated work. And you can test the stability of rigid structures with the help of formulas which are there, because they are rigid structures. They are available in shore protection manual or some of the books which are used for design of marine structures, like by Per Burun. Then semi-rigid structures formulation is there. So I will not go into details because the modeling is not carried out for this. But for rubble mount structures, being a very complex in nature, hydraulic model studies are very essential. So assessment of hydraulic stability of multi-layered rubble mount structure is complex and is governed by hydraulic response of a particular structure to the dynamic attack of breaking or knock-on breaking waves, or maybe say random waves. So the wave forces and the loadings which are exerted by these waves on the armor layer, and what is its response of that structure to that wave loading, is very important. So this is a rubble mount structure. The waves, these are the incident waves. You can see when the wave comes, there will be a run up, and there may be some overtopping also. There may be some transmission of the waves also. So this is called as a rock portion, or called as a core portion. Then a secondary layer is there. Then a main armor layer which takes the brunt of this wave action. And you can see that during the run up, how the hydraulic response is there. And and then this is during rundown process, and during run up process, how the water goes up and goes inside. And this is some sort of a diagram which shows you what sort of a forces are acting. Maybe say gravity force acting, then drag force is acting. Then in that again two types of drag: form drag, surface drag, then the lift coefficient. So computation is very difficult analytically and mathematically. So physical modeling is the only tool with the help of which you can assess the hydraulic stability of marine structure. So when the wave goes up, that portion is called as a run up. When it recedes, it is called as a rundown. Then wave overtopping, wave action prior to breaking, how it looks. Different types of armor layers are types of armor. This is a tetrapod type of block which has been used. Then actual wave breaking. So I can say that design of coastal structure, most of the coastal protection structures like sea dikes, revetments, bulkheads, groins, they are detached or say detached, but they are rubble mount type of structures. These structures are primarily porous structures with multi-layered armors. And they are multi-layered armors. They are subjected to dynamic attack of either breaking waves or non-breaking waves, random waves of varying magnitude over a period of time. And that too, again, the tidal level is also varying at site. So like that, you have to study its stability for different water level conditions also. So design of structures from hydraulic stability consideration is quite complex and cannot be done using simply solving mathematical equations due to non-linear wave structure interaction. So wave structure interaction is totally non-linear because the waves which are attacking, they are also non-linear. That means random waves. Simulation of wave penetration into the porous body by mathematical formulation of a rubble mount structure is also very difficult. So hence simply use of empirical or semi-empirical formulae will not assure the hydraulic stability of such structure against the wave forces acting during lifetime of that structure. So normally we consider the lifetime of such structures at 100 years. So this is a physical model. You can see it here. Thus, physical model is used for assessing hydraulic stability of marine structures or marine rubble mount structures, as flow conditions in natural phenomena are not amenable to mathematical analysis. So which are there? Wave breaking, wave structure interaction, that is which is turbulent. Then turbulent flow passing through the multi-layered porous material. So it is nothing but a scaled representation of a hydraulic flow phenomenon and cannot be disassociated from basic theories of fluid. So in coastal engineering, a physical model is always smaller than prototype. So if you consider a breakwater structure, you can see it here. So this is breakwater. So this portion is called as a root portion. This is called as between root and the end portion is called as a trunk portion. And at the end, it is called as a rounded portion. So trunk portion is tested under the normal attack of waves. So model is laid and it is tested in the random waveform. And a rounded portion is tested under the angular attack of waves, which are coming from the ocean. So this is a wavefilm facility available at CW Paris, was installed at CW Paris under United Nations Development Program and has been extensively used for assessing the hydraulic stability of marine structures which are built in India. So design of marine structures, the hydraulic stability of marine structure is determined based on the expected life of the structure. That means the wave forces that structure has to withstand during its lifetime. So if I consider lifetime 100 years, so what wave height I should consider for its design? And a service life of the structure. That means there will be some life, that means the entire life of that particular structure, and some service life, means after certain years, it may not be that much useful. So you have to restore that structure again. So the wave height for which structure should be withstand is decided by life of the structure for assessing the endurance limit of that structure, and for service life to assess its performance from serviceability point of view. Then again, to determine the wave, what wave conditions are considered, like short term, long term, extreme. I will not go into the details. They are a little bit theoretical things. Then short term means you are considering data for 20 minutes. Long term means about 1 year data, and extreme wave data means you are considering 30 to 50 years of data, and from that 30 to 50 years of data you are determining what will be the design wave conditions. So the same thing what we have done studied for wave mechanics or wave tranquility, the same is useful here, because the wave force is more dominant and is responsible for causing the damage to structures or causing destability. So this is what we have seen earlier. So the severity of scale effects depends on the magnitude of forces of gravity and viscous shear. And they are again based on these rubble mount structures. They are based on an important hydraulic principle called as a Froude's law or Froude's principle, and the models has to be geometrically similar. So these are some of the theoretical things where you can determine what should be the dimensions of the block. So these are theoretical. I will not go into the result. And there is a one very user-friendly formula which is available called the Hudson's formula. It was developed way back in 1950s or so, wherein you can determine what should be the stable weight of an armor layer if you know the design wave height, if you know the density of the material. Then this is what is called as a stability factor, and SR is nothing but the specific gravity of the armor units and the slope at which it is laid, that is called theta. So this is very much useful in evolving the conceptual cross-section of a breakwater structure. So selection of stability coefficient, that KD, is for different types of armor units. Maybe say dolus is there, tetrapod is there, and so on. So it depends on what is the shape of the armor unit, what surface roughness is there when they are placed over each other, what are the degree of interlocking, method of placement, type of waves which are attacking the structure, whether it is breaking, non-breaking, or broken, and at what angle they are coming. So shape of the armor unit is important. Surface roughness is important. What sort of a degree of interlocking it achieves when the waves are attacking. In what fashion they are placed, either uniform fashion, or whether random placement is there, or whether selective placement is there, or whether a special type of placement is kept. So it governs the stability factor. So whether the waves are breaking, non-breaking, broken waves are hitting the structure, angular attack of waves. So these are some of the criteria. And depending upon what type of structure you want to design, whether it is a rigid structure, semi-rigid structure, or flexible structure. So these are the design conditions for which you have to assess its hydraulic stability. So for flexible structure, normally it is designed for a significant wave height. Significant wave height means is the average of the highest 30% of the waves in a given wave train. There are different formulas developed by different research workers. Different types of waves. If it is a plunging wave or surging wave, so what sort of formulation is to be used is given. And even with this type of things, you can determine the size of the armor block, the sublayers, the core, what will be the run up, run down, and all these things. But it needs to be tested in a hydraulic stability, for its hydraulic stability in a wave film facility. So these are some of the formulations. I will not go into the details. They are available on the book, what is called as the Shore Protection Manual or a Coastal Engineering Manual, published by United States Waterways Experiment Station. And based on that, for different types of structures, different stability numbers are established. So a lot of research has taken place in last 70 to 80 years in the field of coastal engineering to understand the nature, what type of waves are there, how its distribution of the waves is there, what sort of a structure will withstand what type of wave conditions, under what water levels, and all these things. So a lot of technical information is available, and knowing that you can assess its stability. So at CWPRS, we do have 3 monochromatic wave film facilities like 40 meter, 50 meter, and 75 meter. Here you can generate only monochromatic waves. That means you can assess the hydraulic stability of marine structure under the attack of non-breaking waves and breaking waves. So you can see here how it is being tested. And you can keep the sensors and you can generate a monochromatic wave. So when the wave comes and hit the structures, there will be some reflected waves. So you can separate out incident and reflected waves with the help of these sensors. You can estimate the reflection coefficients. You can assess the hydraulic stability in a random wavefilm facility with different types of facilities which were established under United Nations development projects. So these are highly complicated systems and costly also. So as on today, it may cost some 2 crores also. So they are very costly facilities. Government can afford to have such facilities and can assess the hydraulic stability of marine structures. So data acquisition systems are there. So various sensors are required. You can separate out incident reflected waves and you can test the hydraulic stability. So evolve conceptual design of coastal protection work by empirical formula like Hudson formula. Construct the physical model of structure in a wavefilm and test its hydraulic stability under design wave conditions. And based on model studies, the cross-section of the protection structure is finalized and is recommended for construction. So conceptual design is carried out. You can see here. So everything is given in book. I will not go into the details of that. So once you know the water level, you know the bed level, bed slopes, seabed material, whatever material and armor, you can work out using that Hudson's formula for a given wave height, what should be the weight of the armor layer. So it has been worked out as a 1 ton if the wave height is 2 meter and the armor slope is 1:2. So you can see weight will be 1.5 to 2 ton. So this was a seawater density of 1.025 ton per cubic meter. Similarly, for different underlayers, secondary layers, its thickness, its weight can be evolved using the formulation which is available. Crest, what should be the crest width? What should be the crest height? Width of the tow berm. Then design of filters. So based on Tarzagi's formulation, you can determine the filters. Maybe says made up of coarse sand. If the material of coarse sand is there, then if gravel, then you can even design the geofabric filter behind such structures, beneath such structures. And you can evolve a cross-section based on this empirical, or we can call it a semi-empirical formula. This is armor layer 1.5 to 2 ton. When the bed level is 2 meter, tide level is 5 meter. The top level of the structure should be about 7.5 meter. Width of the crest about 3.5 meter. Tow berm consists of 150 to 200 kg. But this is based on Hudson's formula, but it needs to be tested in a wavefilm facility. So damages to the rubble mount structures, they are of different type, like breaking of the armor layer, overtopping, causes sliding of the crest slab, or tilting of the capping wall, slip circle failure on the lee side as well as on the armor side, damage to the tow berm, entire failure of the structure because of filter instability, subsoil settlement, core settlement, and so on. So like that, you can design the breakwater structures. Now you can see one of the monochromatic waves. Under monochromatic waves, how this structure is being tested. And this is the random. On the right side, you can see the rounded up breakwater is tested in the random wavefilm facility. You see the wavefilm waves are random in nature. Each and every wave is different. And for rubble mount structures, normally the model scale varies between most relative to most. This is a 90-meter wavefilm facility available at CW. Again, a random wave. This is a wave generating system with a hydro servo system, and a computer is kept in this room. From this side, if you see, it looks like this. The model is laid here. Your wave generation is here. So here you can see it is the seawall at Miria Bay in Ratnagiri being tested on random. So each and every wave is different. Some waves are breaking Before reaching the structure, some are breaking on the structure. Then one of the breakwater which was constructed at Porbandar, having a length of about 1200 meter, was damaged during the severe cyclone which has occurred on 8th and 9th June 1998. And out of 1200 meter length, you can see this is 1200 meter length, about 600 meter distance, for a distance of 600 meter distance, the entire breakwater is washed away. That too from this rounded end. And it was due to the increase in the wave height than the design wave height, and the breakwater was overtopped because of the waves. So measurement constraints in the restoration of breakwater is a very difficult task in front of the coastal engineers, because the exact measurement how the debris has collapsed and taking those levels in sea is very difficult. Removal of such fallen debris from the ocean is very difficult, and restoration by conventional method of such breakwater is a very costly affair. So this is a conventional breakwater, a white tow bar, a tow is there, armor, core, secondary layer, and crest. So this was a damage profile. So we have made the use of this damaged portion to act as a seat for a white tow berm. Earlier the tow berm was about 5 meter. Now we have made it 20 meter. And with this, the hydraulic stability was tested, and we found that the wave height which caused a damage to that rubble mound structure was about 8.4 meter for a storm which might have occurred for a return period of 100 years. That means a storm which has occurred once in 100 years, it has generated a wave height of about 8.4 meter. And this is how, if it is to be restored with conventional type of armor unit, it requires 49 tons of tetrapod. But with 1:1.5 slope. But if you make the use of already damaged profile to act as a tow berm, then weight gets reduced to 15 ton. So there is a drastic reduction. So this new concept of white tow berm was evolved for restoring the damaged breakwater at Porbandar. So construction was going on. Here you can see the white tow berm testing is being carried out, and the construction is, you can see it going outside, and now it is fully restored. So you can see the cost comparison in 1999. If it would have been replaced with conventional type of breakwater, it would have cost 50 crores for 600 meter distance. And whatever CWPRS has recommended with white tow berm technique, its cost is about 38 crores. So there is a net saving of 1200 crores based on the hydraulic model studies carried out at CWPRS. Then beach stability. So I will just keep, these are the various techniques which are used for protecting the beach. Then bulkheads are constructed to protect the coastline. They are vertical structures. Then sea walls are constructed. They are of different type, either a concrete curve type or a gabion type, or maybe say step type or a rubble mount type. You can see here. Then revetments are constructed. They are almost take a shape that of a beach slope. Then groins are constructed. When there is a longshore movement of the sediment, then the groins are constructed perpendicular so that the sand get arrested in between the different groins and a nice beach will get formed. Then offshore breakwaters, whenever there is an onshore and offshore movement, I think Dr. Agarwal sir has already shown you when such offshore breakwaters are constructed, on the lee side of it, Tambola effect will get formed and a nice beach will get formed. Then sand trap sediment movement, artificial reefs, combination of artificial beach nourishment with that of detached sea walls, mild slope sea walls, control the groundwater movement on the beach, which you can do vegetation plantation. You can use the geosynthetic material to act as some sort of a barrier and to avoid the coastal erosion. On islands, normally coral balls or coral cages, they are used. So such type of structures, they are constructed on the islands. because if you want to have a construction of a sea wall, something like that, then transportation of stone will be a big problem because quarrying is not allowed on the islands. So such type of coral reefs or coral balls, they are used and they are partly submerged. The waves which are attacking on these structures protects the beach on the leeward side of those coral balls. So one of the site for what we consider is near Bombay, there is a one ONGC plant at Uran. And so this is that location where the ONGC plant is there. There is a refinery is there. And through underground oil pipelines, the oil from the Bombay High is taken here in a refinery. So this is a plant area, and in front of that about 300-meter portion got eroded. So here you can see how the portion got eroded and that plant was in danger. So you can see vertical cliff type of erosion was there. And the beach slope was very steep. You can see here very steep beach slope. And its testing was carried out at CW Paris in a wave film facility, and the seawall section with 1 to 1.5 ton stones, they were recommended in Bombay. As I told you, for Bombay, the highest height is about 5.2 meters or so. And then the seawall is constructed and it is standing very well. So existing methods, the thing is that existing practices, artificial nourishing marine, user-friendly, however, requires recurring expenditure. Construction of seawall requires heavy equipment, time-consuming. Buoyant constructions, they are useful in arresting littoral drift. Construction by conventional method requires use of heavy cranes, while offshore breakwater requires construction requires uses of barges and hence costly. So when availability of construction equipment, material is not available, heavy equipments like cannot be used at the coast because sufficient beach width is not available for the movement of the construction equipment. Time span in which it is to be constructed is very limited because before the coming of next high tide, you have to construct some structure. Non-availability of sufficient beach, that's what I told you. So at Udwada in Gujarat, there was a school building and that got eroded, and chain of concrete block was a new type of thing what CW Paris has evolved, and it was tested in a wave film facility with concrete blocks chain was made, and offshore detached breakwaters were constructed and after testing, and you can see the wave action on top of it. So you can see so here you can see how these offshore breakwaters which are detached from the waves are breaking on top of the structure. Some of the waves are getting over there, and one of the sediment is getting caught on the inside of it. So after a period of time, you can see this earlier. This was the top. On top of it, the waves were overtopping. A nice beach is getting formed on the leeward side in front of the school building. So you can see a very nice beach is getting. Earlier it was totally removed. So here you can see in 1997 the beach profile was like this. In 2000 it becomes like this yellow one, and in 2000 a nice beach, flat beach is getting formed. So this is how the new techniques, they are very much useful. The beauty of it is that ease in construction, elimination of use of heavy machinery, construction using one-man stone, environment friendly, reduction in construction time, reduction in construction cost, long life, and increased durability. So flexible gabions are also used in providing the coastal protection works. For a particular site, it was tested for a breaking wave height of 2 meter period, 10 seconds. So by conventional method, you can see it requires 1 to 2 ton stone when the wave height was about 2 meter. And with 1 to 2 you can see here. And with the gabions of a size of 1 meter by 3 meter, flexible gabions which are filled with 20 to 40 kg stone. One person can lift 20 to 40 kg stone very easily and can put it into the gabions. And naturally, there is no necessity of having any heavy construction equipment for this. So one of the site in Valsad in Gujarat called as Tithal, where a Swaminarayan temple is there, there was a vertical cliff type of erosion. And the project authorities, they were recommending such type of structure, which was a very costly structure. So CWPRS has recommended flexible gabion type of structure with this type of different gabions kept on top of each other. And it was tested in a wave film facility under the wave height of about 1.6 meter at a water level of 4.5, which prevails at Tithal. So you can see how the construction can be carried out using only one man. Such type of gabions, they can be used. Close-up view of such gabions, it can be have a nice cross section. In step fashion, you can use it. And the constructed wall at Swaminarayan temple, this video. You can see how the stones are placed in gabions, and these act as a seawall. And afterwards, you can know the seawall is quite intact. These are the photographs of rounded of a seawall. It is quite intact. There is no damage to it. Nice beach is also getting formed in front of it. A nice beach is formed. You can see here. In September 2003, the construction was carried out in 2001. And is useful when the beach width is less, stones of sufficient weight are not available in ample quantity at cheaper rates, construction time is reduced drastically, no necessity of heavy equipment like cranes. One man stone, that means 20 to 40 kg can be handled by person very easily, and structure is more porous, and hence it dissipates the more wave energy. So these are some of the conclusions that oceanographic phenomena are complex, varies with time and space, and are dynamic, especially in coastal zones. Site-specific field data is inevitable to understand the various physical phenomena such as wave climate, tidal flows, velocity field in order to finalize the layout of ports, harbors. Physical model studies with geometrically similar scales are essential to assess the hydraulic stability of coastal structures in a wave film. As on today, due to non-availability of reliable numerical model, model scale should be selected such that the scale effects are made negligible and model acts as a nature in miniature. Physical tidal model studies are distorted and are useful in finalizing the alignment orientation of berths, assess the impact of reclamation on surrounding, finalizing the orientation of the guide bund, and so on. Depending on site conditions, availability of construction material and equipment, suitable conventional or innovative coastal protection structure needs to be suggested based on the model studies. And to protect the beaches against the severe threat of erosion and avoid losses of land and damages to the properties, so structures are essential. So it was a very exhaustive topic. Talking something about physical hydraulic modeling in coastal engineering, there are various scenarios or various phenomena for which you have to make its application in finalizing the port layouts, in studying the wave tranquility, in finalizing the alignment of the berths, to study the effect of reclamations on the surrounding area, to fix the orientation of the bund so that the birthing can be possible very easily at the birth, assess the hydraulic stability of marine structures like breakwaters, what are the wave conditions for which it needs to be studied. So it's a very vast topic. Talking something about it within, again, I can say 1.5 to 2 hours is very difficult, but I tried my best to give as much as little knowledge I do have to the participants who are attending this seminar. Thank you, madam. Hello.
Hello. Yes, sir. Thank you for such a wonderful session. I hope all the participants Hello.
Yes, is there are any questions?
I request participants, if you have any question, you can put it in the chat box.
Yes. Hello.
Namaste, sir.
Yeah. Namaste. Rohit, you are listening me?
Yeah, I am.
Yes, it has been a really wonderful session. I have not expected so nice from you, but it was even more than that. You started from the rainfall modeling, rainfall cycle of the earth, thereafter the tides, waves, mathematical model, physical model of tide, then wave, and then to the protection. You have covered almost all the topics very, very nicely with all technical details. It was a wonderful session, and you kept your promise that you took it for 2 hours. Such a long duration, continuously speaking, really very nice to listen from you. Such a wonderful lecture. I am really impressed. Very nice. No need, no word to say more than that.
Thank you, sir.
Aboli, you can continue now.
Yes, sir.
Yes.
So I take this opportunity to propose vote of thanks for the program. On behalf of Civil Engineering Department, I extend my heartfelt thanks to our expert, Engineer Purohit sir, for guiding our participant by elaborating the techniques of physical hydraulic modeling in coastal engineering using suitable case studies. I hope this will surely enhance the knowledge of our participants in the field of coastal engineering. I am very thankful to our management team and participants to make this session successful. Thank you, sir.
Thank you. Welcome.
I request all the participants to fill the feedback link, which is shared in the chat box.